Okay, so the upper part of the screen above the magenta line shows the problem that previous to the one we're about to do, where we found the mass required, the little mass m required here to just get this moving, assuming a static coefficient of friction of 0.5. So now what we're going to do is we are going to have this 1 kilogram mass that we solved for before that's just on the cusp of getting it moving. But then with 1 kilogram on there, we're going to take our finger and give this big M a little bit of push to the right. And so what's going to happen in that case is it's going to transition from being static coefficient of friction to kinetic coefficient of friction, which is typically smaller. And so the mu changes from 0.5 to 0.4. Well, that means that it's going to accelerate. And so what we're going to do is we're going to find the acceleration. So here's a free body diagram analogous to the one above for big M, and it shows these two equal and opposite vertical forces, and then two horizontal forces, a tension to the right that is a little bit longer than the frictional force. This is now kinetic frictional force to the left. And then the free body diagram for little m is downward weight for little m, which is mg, and an upward tension. These two tensions are the same. And so big M is accelerating to the right, as shown, and little m is accelerating down, as shown. So the corresponding Newton number 2's are big M times A is equal to the net horizontal force, which is T minus F sub F. Well, F sub F is mu sub K times the normal force. But the normal force is equal and opposite to mg, and so I can replace n with mg. So I get m sub A equals T minus mu sub K mg. The Newton number 2 for little m is minus m times A, negative because this A is pointing down, equals T minus mg. And so if I solve this for T, bring this mg over on the other side here, T, the tension, is then equal to mg minus ma. So I can take the tension expression from this Newton number 2 and substitute it into this tension that I have for the Newton number 2 for big M, and I get, as a result of that, I get big MA is equal to mg minus ma. This is the substitution result, minus mu sub K times mg. Getting all the A terms over on the left, big M plus little m times little a is equal to g times m minus mu sub K times big M, and then dividing by big M plus little m. A, the acceleration, is m minus mu sub K times m divided by the sum of big M and little m times g. So let's plug some numbers in. 1 kilogram minus 0.4 times 2. Well, this is 0.8. 1 minus 0.8 is 0.2. Divided by 3, kilograms cancel, times 10 meters per second per second. Easy number for the acceleration of gravity. And so 0.2 times 10 is 2, so that's 2/3. 2/3 meters per second squared is the acceleration of both the big M to the right and the little m down, or if you like in decimals, 0.67 meters per second per second.